Okay, so now this is one of the slightly more advanced topics that we are going to look at, which is that we are going to go a little bit into the internals of what a simulation looks like, right? A Verilog simulation. This is primarily because there are a few terms over here that are important to know when you are dealing with Verilog. We will not actually be getting into the details of how Verilog simulators work. Just sort of mentioning a few of the terminology so that you are aware of the kinds of things to watch out for when actually using a simulator. The ultimate sources of truth for how Verilog is supposed to work comes down to the language reference manuals, right? There are a couple of IEEE standard documents that can be downloaded from IEEE Explore, for example. One of them is the standard 1364, which is for the Verilog language reference, and then standard 1800, which is for system Verilog, right? System Verilog in some sense is a superset of Verilog. The documents are similar in some ways, but have also changed quite significantly in terms of the order of how different materials are handled in these two cases. So what I am going to talk about over here is just bring in a couple of concepts. The most important is how the notion of time is handled inside a simulator, right? The simulation is expected to proceed in steps. Right? We have the current notion of time, and there is also something else called a delta cycle, which nominally you at least need to know what the notion of a delta cycle is, because it makes a difference to how you evaluate certain pieces of Verilog code. The events in Verilog themselves are processed in the form of a queue, and a queue is a very specific kind of data structure from computer science, which basically says that as and when new events are generated, I put them into a so-called first in, first out queue, right? I have a list of operations, a list of things that have happened, and I will take them in the time order in which they happened and actually evaluate them, right? Now, there are, as I said, two types of simulation time. One of them is actually the hash delays that we use in order to say, okay, wait for 1 nanosecond or wait for 10 nanoseconds or wait until the next clock cycle and so on, right? But there is also a notion of something called a delta time, which we will get to in a moment, right? Any change in the value of a net, where a net is basically actually a wire in a circuit, but as far as Verilog is concerned, any signal, right, which holds a logical value. Any change in the value of a net is called an event, or in particular an update event, right? And as we already saw, always blocks have sensitivity lists. They are sensitive to these kind of updates. Anytime a net gets updated, the always block has to then go in there and re-evaluate, right? All the processes that are sensitive to a particular update event. So if there is a signal called A, only the processes that are sensitive to A are going to get executed, right? In other words, if a wire is not connected to a particular always block, right, there is no reason to go and re-evaluate that always block when A changed. I need to look for what that block is sensitive to in order to decide whether I need to go in and re-evaluate it. Okay. And one very important factor over here is that the order of execution of these different blocks, let's say that I have 3 different blocks that are all sensitive to a signal called A, I cannot guarantee the order in which those 3 blocks are going to get executed or updated. This is a crucial part of the so-called concurrence story of Verilog, right? Concurrency basically means that the 3 blocks that are dependent on A are effectively independent of each other, and the exact order in which I need to go and evaluate them is not specified by the language. Okay. Potential source of confusion, potential source of bugs. If you find that there is something in your code which works correctly only if you write the always blocks in a particular order, it's almost certainly a sign that there is actually a big bug in your code and you need to fix that. Time by itself is something which is maintained by the simulator as a number, right? It's a monotonically increasing quantity, so usually we think of it as some kind of an integer which is basically increasing, and it has some kind of resolution, which is the time precision that we specify in the time scale. This is used in order to order events. I can decide whether one event happened before or after another event based on the time at which the events occurred. All events that occur are placed on an event queue ordered by the simulation time, so that, as I said, first in, first out, right? The first event in terms of time is the one that comes out first. But what that means is, if some other process block comes in and creates a new event that needs to fit in front somewhere in the queue, it does go in to the particular time slot where it was supposed to get activated. Okay. So these are so-called priority queues. If some event comes along with a high priority, meaning that it's at a very early time in the that I need to process it, it will go close to the front of the queue or to the top of the queue, depending on what the next simulation time step is. And putting events into the queue is what's called scheduling. So this term scheduling is something that you will come across when you are talking about Verilog simulators. How events get put onto the queue and how they are processed is part of the problem of how you schedule events and you actually run the simulation. Now, the Verilog language reference manual actually defines a number of different types of events. The most important one as far as we are concerned is the so-called active events. This is when a signal actually changes value. Let's say I have a signal called A and I assign a value A equal to 1. That becomes an active event that is then going to trigger a bunch of other evaluations. The A equal to 1 immediately goes and sits somewhere on the queue. Since there is no delay associated with it, it's going to go and sit right at the present time instant. If I give hash 10 A equal to 0, it's effectively creating an event for 10 time steps into the future, right? And it will go and sit on the queue, but any other event that needs to come in now is going to come and sit in front of this hash 10 A equal to 1 or A equal to 0, okay? So inactive events are things that are scheduled at the present time step, but after all active events. How do such inactive events come in? Because they are triggered by other things not related to actual explicit assignments, right? This is once again a detail of how it's defined in terms of the internals of Verilog. Non-blocking assignments, of which so far we have basically not looked at it at all. We will talk a little bit about it when we get to sequential logic, right? Non-blocking assignments, however, do also result in a certain type of event update, but Verilog explicitly handles these differently from the active events, right? And then of course we have already come across monitor events, right, where essentially anything that changes is basically also flagged as an event that needs to get processed. So the $monitor by itself also creates tasks that need to actually get executed, right, and those are also get scheduled as events that need to actually get run or updates that need to get run. They are used for debugging and tracing. And as I said, you could finally have future events where basically if I have something like hash 10 A equal to 1, it says okay, this is going an active event, but it's going to be something scheduled at a future time. Now this already looks a little bit confusing, right? And for the most part you do not need to worry too much about it, especially because if you go into system Verilog, it turns out that it has many more subdivisions of these event types. Unless you are actually getting into the game of how do I implement an event driven simulator, for the most part you do not need to worry about any of these things, right? Especially when you keep in mind that at the end of the day, most of these events and the way that these events are processed become more relevant for the test benches and how you create certain kinds of tests. If you actually need to use these kind of complicated structures in your synthesizable code, very likely there will be bugs that are going to be hard to trace and that you will not be able to connect with what is actually happening in the real hardware. So there is a notion of a delta cycle once again, which is primarily a VHDL concept, but it's a little bit useful to understand in Verilog, so I'm going to just briefly talk about it over here. What it says is, let's say I have these three assignment statements, right, which are performing computations based on changes in two inputs A and B, right. As we can see over here, anytime that A or B changes, N1 is going to get re-evaluated. Now what that in turn means is, whenever N1 gets evaluated, that has effectively created a new event. But when does that event happen? At the same time instant, right? Time has not advanced. It's not like I have gone to a time instant of 1 time unit. I can't say I am waiting for 1 nanosecond because there is no delay associated with this. It's saying, okay, if the current time is 0, I am still at time 0 but n1 has changed. Okay, so what if n1 changed? Well, it means I need to go in and re-evaluate n2 and I need to go in and re-evaluate y as well, because both of them have n1 on the right hand side. Okay, fine. Now I go in there and I decide I am going to re-evaluate n2, right? The interesting thing is I could also have chosen to re-evaluate y instead, because after all n1 is on the right hand side of both of those, and the order in which I should do these things is actually not specified by Verilog. Having said that, most simulators are smart enough to see that yes, there is also a transitive dependency from n1 to n2 and then to y, so they would probably end up doing n2 first, right? So n2 would go into a delta cycle. Why do I call it a delta cycle? Because it is a time step which is slightly different from the time at which n1 got evaluated, but is not actually resulted in time increasing as far as the simulation internals are concerned, right? So it's like a simulation delta. There is no actual increase in the amount of time. It's just that these are different steps that happen one after the other. First n1 gets evaluated, then n2 gets re-evaluated, then y gets re-evaluated. Each of those is happening within deltas and all of them effectively happen at the same time instant, but in sequence one after the other. So the notion of delta cycles can be useful to sort of understand how these things get ordered. That's the main thing to keep in mind. Once again, blocking versus non-blocking is something that we'll talk a lot more about when we actually talk about modeling sequential logic. For now, the important point is simply this. In general, we'll be using non-blocking assignments in order to actually model how hardware works. In the context of events, why it is useful to understand is basically this, right? We are talking about, let's say, a change in D, and what it says is that everything inside this always block, whenever there was a change in the clock, it will first take the value of D and put it into Q1 and immediately take that value of Q1 and put it into Q2. So effectively what this will end up doing is that Q2 will just get this value of D, right? That's usually not what we want in practice. What we want is that this is supposed to be more like a shift register, right? Where Q1 takes whatever was the old value in D, Q2 takes whatever was the old value in Q1, and that is exactly what is achieved by using a non-blocking assignment, because they go into a queue after all the active events, and therefore this update is going to happen only after both the D as well as Q1 update values are registered as events into the queue. So as I said, this is a slightly more advanced set of topics, but they are useful to know because you need to keep in mind what exactly the Verilog simulator is doing. When you go and run through and you try to debug your Verilog code, there can be places where you find that either the notion of how simulation is working or of what is actually happening at a given instant in time is not particularly clear until you sort of start thinking in terms of, okay, how are these events actually getting propagated inside the system, right? Having said that, if you find that the order of events and the way that these things are described makes a difference to your final code, there is a good chance that you can probably simplify your code or modify it in a way such that it should work independent of those delays. As a rule of thumb, as I mentioned earlier, using delays in test benches is a good use of delays. You need to use it in order to actually decide how stimuli are being applied to the DUT. But if you need to have delays inside your module that is actually going to be the design that you are creating, very likely chances are that there is some issue that you are going to face. In particular, keep in mind that #1 or #5 or #10 is just a number as far as the Verilog simulator is concerned. It does not actually correspond to an equivalent change in hardware. So these are models, they are not by themselves reality, and anything that you do by fixing some aspect of the simulation algorithm may not imply correctness in the hardware. Okay. So always keep this in mind when you write Verilog code. You should not need to modify code in order to pass a simulation by saying, okay, this is because of some issue related to how the simulator algorithm worked and I can fix it by making this change in the code. Chances are that that's actually revealing some deeper misunderstanding of what's happening in the actual underlying hardware.